what is all this? Like, fundamentally, what's the absolute smallest bit everything's made of?
It's the ultimate question, isn't it? And yeah, physicists are definitely still wrestling with it. We keep digging deeper.
And that digging, that whole journey is what we're diving into today, using these sources you've gathered, articles, notes, all that good stuff.
Exactly. The plan is to sort of unpack the standard model, figure out these tiny building blocks, the particles, the forces.
Without getting totally lost, hopefully. We want to pull out the really key ideas, maybe some surprising bits too, so you can actually, get a handle on it.
That's the goal. Clarity, not confusion.
Okay, so fundamental particles. Where do we start? The sources say they're the absolute basics, right? Nothing smaller inside them.
As far as we know, yes.
Yeah.
That's the definition. And the framework we use to organize all this knowledge is the standard model.
The standard model. Okay. And it splits things into two main types.
Broadly speaking, yeah. You've got fermions and bosons.
Fermions and bosons. What's the, quick difference?
Okay, think of fermions as the matter particles. They're the bricks, the stuff that makes up everything you can touch.
Got it. The substance.
Right. And bosons. They're mostly involved in the forces, carrying interactions between the fermions. Plus, there's one special boson, the Higgs.
Ah, the Higgs. We'll get to that. But there's something about their spin, too. That sounds fundamental.
It really is. Spin is this intrinsic quantum property. Fermions have half-integer spin, like 1/2. Bosons have integer spin 0, 1.
And that actually changes how they behave.
Massively. Fermions obey something called the Pauli Exclusion Principle. Basically, two identical fermions can't be in the exact same state in the same place.
Ah, that's why electrons fill up shells in atoms, right? They can't all pile into the lowest energy level.
Exactly. It forces structure. Bosons, though, they don't care about that rule. You can cram loads of identical bosons into the same state. Think lasers, tons of photons acting as one.
Okay, cool difference. So let's dive into the fermions then, the matter stuff. The sources split them up further.
They do. Two main families within the fermions, quarks and leptons.
Quarks. Okay, I know those are inside protons and neutrons.
That's them. They're fundamental, and the key thing is they feel the strong nuclear force.
The really powerful one holding the nucleus together.
Yep. And because of it, they have this weird property called color confinement. You never, ever find a quark on its own.
Never? Why not?
The strong force actually gets stronger the farther apart you try to pull them. So they're always bound together inside composite particles called hadrons.
Wow, okay. That's clingy. So how many kinds of quarks are there?
There are 6 flavors, and they're grouped into 3 generations. Each generation is heavier than the one before it.
Generations, like versions 1, 2, and 3?
Kind of, yeah. Generation 1 is the up quark and the down quark. These are the lightest and make up protons and neutrons, everyday matter.
Right. A proton is 2 ups and a down.
Perfect. Odd. And a neutron is 1 up, 2 downs odd. And they have these weird fractional electric charges. Up is plus 23, down is negative 13 charge.
Fractional charge, not like the electron's whole -1 charge.
Nope. That's unique to quarks. Really threw people for a loop initially.
I bet. Okay, what's generation 2?
Generation 2 has the charm quark and the strange quark. Heavier, more exotic. They were common in the very early universe, and we make them in particle accelerators now, but they decay super fast into the lighter ones.
Strange quark. Did it do weird things?
Huh. Yeah, its discovery involved particles that live longer than expected seemed strange. The name stuck.
Makes sense. And generation 3, even heavier.
Much heavier. You've got the top quark and the bottom quark.
Yeah.
And the sources really stress this. It's the heavyweight champion.
How heavy?
It's the most massive fundamental particle we know. Its mass is comparable to an entire gold atom.
Whoa, hold on. A single particle weighs as much as an atom with, 79 protons and neutrons plus electrons?
Crazy, right? It's incredibly massive. And because of that, it decays almost instantly. It was the last quark to be found.
I can see why. So all these quarks, they have fractional electric charge, spin 12,
right.
Anything else.
They also have something called color charge. Nothing to do with actual color, it's the charge for the strong force. It comes in red, green, and blue. Antiquarks have anticolors.
And the hadrons they form have to be colorless?
Exactly. The combination always neutralizes the color charge, like mixing light.
Okay. And you mentioned hadrons are composite particles. What kinds are there?
2 main types. Baryons are made of 3 quarks. Protons and neutrons are baryons. Since they're 3 spin 12 particles, baryons are fermions.
Makes sense. And the other type?
Mesons. They're weirder, made of 1 quark and 1 antiquark. Pions are an example. And because they have a quark and an antiquark, their spins add up to an integer, so mesons are actually bosons.
Huh. A matter particle made of quarks that acts like a force carrier. Sort of. Okay, mine's slightly bent. Let's move to the other fermion family, leptons.
Right? Leptons. The key difference, they don't feel the strong nuclear force at all.
Ah, so they can be found alone.
They can. The most famous one is the electron. Stable, -1 charge, -1e, orbits the nucleus. Crucial for chemistry.
And leptons also come in 3 generations.
Yep, same structure.
Yeah.
Generation 1 has the electron and its partner, the electron neutrino. Neutrinos are super weird, almost no mass, no charge, barely interact with anything.
Almost no mass. I thought they were massless.
That was the original thought. But experiments, especially studying neutrinos from the sun, showed they do have a tiny mass. It's a big deal, actually. It means they can change type, oscillate.
Oscillate, like change flavor.
Exactly. Electron neutrinos can turn into muon neutrinos or tau neutrinos as they travel. It was a major discovery.
Billions passing through me right now, you said? And changing identity. Okay.
It's pretty wild. Generation 2 gives us the muon, which is like a heavy electron, about 200 times heavier, and the muon neutrino. Muons are unstable, decay quickly.
And generation 3, let me guess, even heavier.
You got it. The tau particle, about 3,500 times heavier than the electron. And the tau neutrino. Tau is also unstable, decays very rapidly.
So electrons, muons, TAS all have -1 charge. Neutrinos are neutral. All are spin 12 fermions. Don't feel the strong force.
You've nailed the key points. They interact via the electromagnetic force if they're charged, and all of them interact via the weak nuclear force.
Okay. Fermions, quarks feel strong force, confined. And leptons don't feel strong force. Got it. Now, the bosons, force carriers, mostly.
Mostly. They have integer spin, remember, and don't obey Pauli exclusion. The force carriers are specifically called gauge bosons.
Gauge bosons, like for electromagnetism.
That's the photon. Massless, no charge, spin 1. It interacts with anything that has electric charge. Because it's massless, the electromagnetic force has infinite range. Light, chemistry, it's all photons.
Okay, and the strong force holding quarks.
That's mediated by gluons.
Yeah.
Cost key. Also massless, spin 1, no electric charge. But here's the twist. Gluons carry color charge themselves.
Wait, the force carriers also have the charge they mediate, unlike photons.
Exactly, that's huge. It means gluons interact with quarks, but also with each other. This self-interaction is what makes the strong force behave so strangely, getting stronger with distance, causing confinement.
Ah, that makes sense now. And it's short range.
Very short range. Only effective inside protons and neutrons, about 10 eurometers.
Okay. What about the weak force? Radioactive decay and stuff.
Mediated by the W and Z bosons, W plus W bash and Z grease. Now these guys are different. They are massive. Really heavy, actually.
Massive force carriers. Doesn't that affect the range?
Absolutely. Their large mass makes the weak force extremely short-range, even shorter than the strong force, around 10 ariometers, and it makes the force seem weak at low energies.
So heavy messengers can't travel far. Makes sense. And what do they interact with?
Everything. All quarks and all leptons feel the weak force. The W bosons carry electric charge, +1 or -1. The Z is neutral. They're crucial for things like beta decay, where a neutron turns into a proton, and for nuclear fusion in stars.
Okay, so photon for E and M, gluons for strong, W and Z for weak. 3 forces down. But you mentioned another boson, the Higgs.
Ah, yes, the Higgs boson. It's different. It's a scalar boson, which means it has spin 0. It's not really a force carrier between particles in the same way.
So what does it do? It's famous for mass, right?
Exactly. It's the particle associated with the Higgs field. This field is thought to permeate all of space.
A field everywhere, like an invisible syrup.
That's a common analogy.
Yeah.
And fundamental particles get their mass by interacting with this field. The more strongly they interact, the more inertia, the more mass they have.
So particles that interact a lot are heavy, like the top quark.
Right. And particles that don't interact at all, like photons and gluons, remain massless.
And the Higgs boson itself is like a ripple or excitation in that field.
Precisely. Finding it in 2012 at CERN was massive news because it confirmed this mechanism for mass generation, which was a cornerstone prediction of the Standard Model. It has a mass itself, around 125 GeV-tar, no charge, spin 0.
Okay, so it gives mass to quarks, charged leptons, W and Z bosons, but not photons or gluons. Does it interact with neutrinos?
That's complicated. In the simplest Standard Model, neutrinos are massless and don't interact with the Higgs. The fact that they do have mass means there's something more going on there, something the basic model doesn't capture.
Another mystery. Okay, let's quickly recap the 4 forces then, based on what we've covered.
Sure. Strong force, strongest, gluons, very short range, acts on color charge. Electromagnetic, Next strongest, photons, infinite range, acts on electric charge. Weak force. Weaker, massive WZ bosons, very short range, acts on all quarks and leptons.
And the fourth, gravity.
Gravity. It's mediated by a hypothetical particle, the graviton. It should be massless, spin 2. It's the weakest by far at the particle scale, but has infinite range and acts on mass energy.
Hypothetical, so we haven't found it.
Nope. And this is a really big point. Gravity is not part of the standard model.
Wow. The force we experience most obviously isn't in our best particle theory?
It's the elephant in the room, really. A major gap. Before we get to the model's limits, though, just quickly on antiparticles.
Right. The opposites.
Every particle has one. Same mass, same spin, opposite charge. Electron has the positron, +1 charge. Proton has the antiproton.
And if they meet?
Annihilation. Poof. Yeah. Pure energy, usually photons, following Ipsic-op.
Classic physics. Okay, so the standard model. It sounds amazing predicting all these particles.
Its successes are huge. It predicted the W, Z, gluons, charm, bottom, top quarks, the Higgs, before they were found. That's incredible predictive power. It provides this consistent mathematical framework for almost everything we see in particle experiments.
Almost everything. But you mentioned gaps. Big ones.
Yeah, it's definitely not the final word. It's incomplete.
Low gravity.
That's number one.
Yeah.
It just doesn't mix with quantum mechanics as described by the standard model. Then there's dark matter and dark energy.
The stuff that makes up most of the universe.
About 95% of the universe's energy density. The standard model only describes the ordinary 5%. It has nothing to say about dark matter or dark energy.
That's kind of embarrassing for our best theory.
It is a bit humbling. Then there's the neutrino mass issue we touched on. The basic model predicted massless neutrinos. We know they have mass, but the model doesn't elegantly explain why or how.
What else?
Why is there so much more matter than antimatter in the universe? The Big Bang should have created equal amounts. Where did the antimatter go? The standard model has mechanisms for asymmetry, but not nearly enough to explain what we see.
Okay.
There are technical problems, too, like the hierarchy problem. Why is the Higgs mass so much lighter than the scales associated with gravity? And why are there exactly 3 generations of particles? Why not 1 or 5? The model just puts these things in. It doesn't explain them.
So it describes what is there incredibly well for the 5% we know, but not why it's that way. And it completely misses gravity and the dark stuff.
That's a pretty good summary. These limitations are what fuel the search for physics beyond the standard model.
What kind of ideas are out there? The sources mentioned some.
Yes, several big ones. Supersymmetry, or SUSY, is a popular idea. It suggests every fermion has a boson superpartner, vice versa. These new particles could potentially be the dark matter.
Superpartners. Okay. What else?
String theory is probably the most famous. It replaces point particles with tiny vibrating strings. It's mathematically complex, but one big appeal is that it seems to naturally include gravity in a quantum way.
A possible theory of everything.
That's the hope for string theory, yeah. Then you have grand unified theories, GUTs, trying to merge the strong, weak, and electromagnetic forces into one single force at very high energies, like in the early universe, and ideas about extra dimensions of space.
Lots of avenues being explored then. It sounds like the standard model was this incredible peak we climbed, giving us a fantastic view, but also showing us how many higher peaks there are still covered in clouds.
It's a great way to put it. It's a phenomenally successful, effective theory for the energies we can currently probe, but it clearly signals that there's a deeper reality underneath.
And it really brings it home that this isn't just abstract math. It's about the fundamental rules of our reality, the stuff you're made of, the forces holding you together.
Absolutely.
So thinking about those clouds, those limitations, here's something to chew on. Given that 95% of the universe dark matter, dark energy lies outside the standard model, and gravity isn't included, what do you think is the biggest secret hiding in that missing piece? What mind-blowing truth about the cosmos might we uncover when we finally figure out that other 95% or quantum gravity?